So, welcome you back. So, in the last lecture, I gave you introduction of statistical inference problems, and then I said the statistical inference problems can be broadly classified into two subtopics. One kind of problems are estimation problems, the second kind of problems are hypothesis testing problems. And then we also said that statistical inference problems could be essentially of two types. One is the parametric statistical inference problems, one is a non-parametric statistical inference problem. What happens in parametric statistical inference problem is, you know that the distribution of the sample, which is the data which you have, belongs to a certain family where the functional form of the distribution is known. So, for example, functional form of PDF may be known, except that that PDF may be having an associated parameter which may be unknown. So, that was parametric statistical inference. Now, in non-parametric statistical inference problems, your f is completely unknown. At the most, we may know that it is either discrete or continuous. And then we described what we mean by a estimation problem. Then we said our goal is to find an estimator for which risk is small or as small as possible. Then we said that it is not possible to get estimator which minimizes the risk for every parametric point theta. So, what you try to do is try to restrict your class of estimators by putting some reasonable conditions on the estimators which you want. You see, if you see the reason why we are not able to find best estimators is because if you have to minimize the risk only at one point, you can use a constant estimator, and that constant estimator gives you, so for example, if your constant estimator is 1, then it gives you the minimum risk at the point theta is equal to 1. So, at theta is equal to 1, the constant estimator minimizes the risk which does not use data. So, at different constant points or different parametric points, different constant estimators minimize the risk. So, in that sense, it is not possible to find the best estimator. So, what you do? You try to put certain restriction or reasonable restrictions on the class of estimators. So, in the last course, a reasonable restriction which you said was that I will use only unbiased estimators. Now, when you have restricted yourself to unbiased estimators, then you saw that it is possible to find the best estimator, which you called as uniformly minimum variance unbiased estimator. Now, invariance is another reasonable restriction which can be used to restrict the class of estimators under consideration. So, let us talk about the invariant estimation in the next few lectures. So, let us see the how does the model looks like. So, typical model looks like you have a data x1, x2, xn. This has a distribution function f which belongs to P, or f belongs to f theta, theta belongs to capital theta. So, this is the situation which would happen in the parametric statistical inference problem. This is a typical non-parametric setup. Now, mostly we will deal with a situation where we have a parametric setup. So, that means your distribution is characterized only in terms of unknown parameter, and the form of distribution function is known to you. So, what you have is you have a estimate g theta which you want to estimate. So, what you have over here is a P. P is basically the class of distribution under considerations. Now, in the parametric setup, this P is characterized by unknown parameter theta which belongs to capital theta. So, this capital theta only tells me what are the distributions under consideration, because functional form is known. So, f theta functional form is known, so only unknown quantity is theta. So, you have a P, and then you have action space which would normally be the collection of all those possible values of g theta such that theta belongs to capital theta. So, to avoid any confusion, let us only deal with parametric setup, so that I do not have to write down this p all the time. I just write down theta, because this theta, which is we call as a parametric space, determines the distribution under consideration, because functional form of f theta is known. Then you have xn space, because you are trying to estimate g theta. So, what should be your estimate? Estimate will be one of the values of g theta as theta varies over capital theta. And then you have a loss function given to you. So, typical estimation problem is described by this triplet: parametric space, xn space, and the loss function. Now, what does the invariance says? Now, suppose two problems have a same formal structure. That means theta is same, A is same, L is same, and estimate is also same. Then the invariance principle says that you should use the same decision rule in the two situations. So, my goal is to estimate g theta based on the data x. Let me call this chi as the sample space. What is a sample space? Sample space is nothing but space of possible values of the data, x equal to x1, x2, xn. So, this would normally be a subset of n dimensional Euclidean space Rn. A is my xn space, L theta A is the loss function. Now, if you recall your last lecture, I had said if L theta A is convex, then you can consider only non-randomized decision rules. So, you do not have to consider the randomized decision rule if L theta is convex, and convex functions looks like a reasonable class of loss functions. So, from now on what I will do is mostly I will deal with situation where my loss function is convex, so that the estimators which I consider are only non-randomized. So, I will not be talking about the randomized estimators anymore. Now, one basic assumption which we made is, if you have two xn's which are different, then they cannot have the same loss function for every theta. So, if A1, A2 belonging to A are distinct, that means you are talking about two distinct xn's, then at least at some parametric point, the loss in taking xn A1 and loss in taking xn A2 should be different. Then there exists a theta naught belonging to capital theta, such that L theta naught A1 should be same different as L theta naught A2. Now, that looks like a reasonable assumption, because otherwise you would say that you are in a situation where you have two different xn's, for them the loss is same for every theta. So, taking xn A1 is as good as taking xn A2, that is what it means. So, if that is the case, I would like to eliminate one of the xn's, because the two xn's are equivalent in that case. So, this looks like a reasonable assumption, so which is what I will make throughout. Now, let us look at what is the principle of rational invariance means. So, what it says is, principle of invariance says that my final xn should not depend on in what units you are measuring the observations. So, whether you take your observation are in minute or seconds, the final xn should correspond, except that xn should be xn of minutes should be converted into xn into seconds. So, the xn's taken in an estimation problem should not depend on units of measurement or any other arbitrary chosen incident. So, whether you measure in inches or centimeters, the two actions should correspond. That is what it means. Now, then invariance principle says what does principle of rational invariance says? It says that if you have two problems, somebody is measuring an observation in, let us say if it is height, somebody is measuring height in inches and somebody is measuring height in centimeters. So, that is the only difference which is there. But if you measure in height in inches or if you measure height in centimeters, as long as my formal structure of the problem does not change, theta AL does not change, then the two actions should correspond. So, that means whatever action I take in case of inches and whatever I take in terms of centimeters, they should correspond, except that you have to convert one action in terms of inches or centimeters, depending on what kind of a transformation you are making. So, invariance principle says if two problems have a same formal structure, then I should use the same decision rule also, same estimator. If two estimation problems have the same formal structure, in terms of theta A L. So, that means your theta is same, the class of distributions remains the same, action space remains the same, and loss function also remains the same. Then I should use the same decision rule in both the situations. Then the same decision rule or same estimator, in decision theory estimator is called decision rule, should be used in two problems. Now, these two principles look like very reasonable principles, and what we will do is we will use these two principles in certain estimation problems to reduce the class of estimators under consideration, because they look like a reasonable restrictions which one should have. What it says is if you are measuring things in terms of different units and your formal structure does not change, then I should use the same decision rule as well as the two actions should correspond. So, to understand this, let us consider one example. So, suppose my data is only one observation, x is normal theta 1, where theta belongs to R. So, what is my parameter space over here? The parameter space is R, and suppose I am interested in estimating g theta is equal to theta. Now, let us consider y is equal to x plus 1. So, I made a certain transformation. Now, this transformation may be considered as changing the units of the original observation into something else. Before that, let me describe the whole estimation problem over here. And suppose L theta A is the squared error loss function A minus theta whole square. So what is my Xn space over here? Xn space would be collection of all possible values of g theta, which is nothing but whole R. So my Xn space becomes R. I take my loss function to be L theta A minus theta whole square. Now these are convex loss function in A for every theta. You can differentiate it twice. The double derivative turns out to be 2, which is greater than 0, so it is a convex loss function. And in fact, you can see this loss function looks like this. So this is L theta A, this is A, it is minimum 0 at the value A is equal to theta. So when your Xn A corresponds to the true theta, the loss is 0. As you move away from A, as you move away from theta, the loss increases. So it looks like a reasonable loss function. A belonging to A, theta belongs to theta. So I have over here an estimation problem where theta, A, and L. Now, so this is a scenario 1. Now somebody says that, look, you are measuring everything in terms of x. I'll not measure x, I'll measure x plus 1. X plus 1 may correspond to certain transformation which may be treated as change in unit of measurement. So I am, rather than x, I am doing y is equal to x plus 1. Now note that if x is normal theta 1, x plus 1 would have normal eta 1. What is the eta? Eta is nothing but theta plus 1, because x has normal theta 1, so x plus 1 would have a normal theta plus 1. So now my parameter becomes eta, which is nothing but theta plus 1. What is the class of distributions over here? So what is my theta star? Theta star is the space for estimating eta. So theta star is nothing but again whole R, because if my this small theta was taking any real value, theta plus 1 also will take any real value. So my theta star is same as R. So I see theta is same as theta star. But what is Xn space? Xn space is collection of all possible values of eta. If theta takes real value, theta plus 1 also can take any real value. So my Xn space also remains the same. So let me call this as A star, which is same as whole R. So theta star denotes the Xn space, theta star A star denotes the parameter space and Xn space for this problem when you are interested in estimating. What is L eta A? Let me call this as L star eta A. L star eta A I take as same, so except that A plus 1 minus theta plus 1 whole square, right? So this is what my L star eta A becomes. So what? So let us consider, or in other words, I can consider A minus eta whole square. That is what my loss function is. So what is happening over here? This is scenario 2. So what is happening under scenario 1 and scenario 2? What I see is theta A L is same as theta star A star and L star. So that means the two estimation problems have the same formal structure. So what I should do? I should use the same decision rule. So invariance principle says I should use the same decision rule or the same estimator. So if I'm using the non-randomized estimator, it says my n estimator under y should be same as, so let me delta naught star y. So if I'm using delta naught for estimating theta over here, I should use the same estimator over here for estimating eta. So that is what invariance principle says. What is the principle of rational invariance says? It says, if you look at, in the first problem you are estimating theta, and second problem you are estimating theta plus 1. So what should happen is, if you take delta naught based on x plus 1, you should be using, that should be same as, so this is, so what you should have is delta naught of, delta naught star of y should be nothing but, so delta naught star y estimates theta plus 1. So that should be same as the estimate which you get from here, and since the estimators are same, so that should be same as delta naught of x plus 1, because this was an estimate based on x, estimate of theta based on x plus 1. So what do you get? You get delta naught star of x plus 1, and since delta naught star should be same as delta naught of x, so that means delta naught of x plus 1, delta naught of y, delta naught star y should be same as delta naught of y, should be same as delta naught of x plus 1, which implies that delta naught of x plus 1 is same as delta naught of x plus 1. So my estimator should be such that it satisfies this. There was nothing very special about x plus 1 over here. I could have chosen x plus c for any constant c. Again, the formal structure remains the same, because x plus c then would have a normal eta c1, where eta c is nothing but theta plus c. If theta belongs to R, theta plus c belongs to R. So my parameter space would have remained the same. So xn space also would have remained the same, and if loss function remains the same, then I should get delta naught of x plus c same as delta naught of x plus c. So in general, in this problem, it makes sense to talk about considering estimators of the type delta naught, which satisfies this for every c belonging to R and for every data point x. So you can take, since this happens for every c, you take c is equal to minus x, because for any c, the formal structure of the two problems remain the same, because this becomes theta plus c only. So I take c is equal to minus x, so I get delta naught of x is equal to x plus delta naught of 0. I take c is equal to minus x. So what do you get? So that means now this would be some constant, delta naught may vary, so this is same as delta naught x is equal to x plus c. There may be some constant. So what it says is, I should only consider those estimators which are of the type x plus some constant c. So you see, the class of estimators could have been very big, but it says I can reduce it to only estimators of the type delta naught. So it says it is enough to consider estimators of this type. D is equal to D delta c, so c belonging to R, where delta c x plus c. Now once you are convinced that only I should consider these kind of estimators, there is a possibility that you may be able to get a best estimator within this class. So here, the principle of invariance helps me in deducing the class of estimators under consideration. As a consequence, I may be able to find a best estimator. So what is happening? What was happening over here? In the original observation X, I applied certain transformation. In fact, I could have put over in any C. So in fact, I applied a group of transformations or a set of transformations. Under those set of transformations, my distribution does not change.